Good morning, friends. It gives me immense pleasure to be here again in this morning to take the class related to the aircraft stability and control, which is related to neutral point and static margin. As you know, I am Dr. Y.D. Dwivedhi, professor from Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. In my previous classes, I have discussed about the aircraft static stability. I have discussed in that we have two types of aircraft stability. One is the static stability, another is dynamic stability. In my previous classes, I have discussed about static stability. So what is the static stability? Static stability is the ability of any aircraft when it is get disturbed by some external forces. These forces may be the gust from the wind or any atmospheric turbulence. If it occurs on aircraft, the attitude of the aircraft will change. After removal of this external forces, if the tendency of the aircraft is to revert back to its original position, then we can say that the aircraft is statically stable. Here we are not considering after how much time it is coming to its equilibrium or original position. But when we talk about dynamic stability, then we have to see that after how much time this aircraft is going to come to its original position. Here in today's class, I am going to discuss these topics. They are the introduction to the aircraft, introduction to the aircraft stability and control, then neutral point and static margin, determination of the neutral point of the aircraft, then maneuvering point. These points I am going to discuss for the next half an hour with you, and hope this will be quite useful for the learners who want to study the aircraft stability and control. First, in introduction, I will start with my Man Ki Baat. As you know, that for today's points are neutral point, static margin, and this maneuvering point. So before I go for this topic, as I have told you just now that there are two types of stability. So one is static stability. If I talk about the static stability, we have two types. So static stability and another is the dynamic stability. If I talk about the static stability, and I am only talking about this, we have here three conditions for the static stability. One is the statically stable, another is statically unstable, third one is statically neutral stable. So in my previous classes, I have very much discussed about the static stability. I have shown you just now, and just I am showing you again here. This is the aircraft. If the aircraft is flying in the steady state flight, there is no disturbance. Aircraft is very smoothly, it is flying. As and when a gust from any direction it comes and it is hitting, I am assuming that it is from the bottom. If the aircraft is experiencing this additional gust of the wind, this will try to make nose up. Once this force is applied, this additional force will disturb the aircraft attitude. Previously it was in steady state flight. Now it will change its orientation and it will now, if it is from the bottom wind, the nose will be up. This nose, if there are three types of actions may aircraft face. One is either it will remain in the same position it is flying, disturbed position, either it is going upward, and next one is it is going towards its equilibrium or original position. So if after removal of this external forces, or when the gust is reduced or it is eliminated, there is no turbulence of the wind speed, whether aircraft tendency is there to remain in the same or it is in the equilibrium, it is trying to or it is tending towards moving to the equilibrium position. If it is tending towards reaching towards the equilibrium position, we can say that it is statically stable. If it is disturbed and it maintains the same attitude, neither it is increasing nor it is decreasing, angle is remains same and it is flying, we can say that it is a neutral stable. And if after disturbance you remove the forces and it is going further, nose is further going up, this is called statically unstable. Statically unstable is very, very dangerous. No aircraft should be statically unstable. Otherwise, aircraft you cannot control. But statically neutral stable is acceptable. But most of the passenger aircrafts, they are statically stable. So these are the part of the statically stable. If I talk about the dynamic stable, so for the dynamic stable, if aircraft is flying from here like this, wind is coming, a additional wind, or this is called the unwanted gust, is hit the aircraft, nose has gone up. Whether with respect to the time, how much time it is going like this, it is called vibrations. Okay, so it will nose up, down, nose, it is, and after some time t, few seconds, if the aircraft is coming to its equilibrium position, we can say that this aircraft is dynamically stable. If the aircraft is not coming at all, it is going like this, every time it is maintaining same amplitude with so much time, it is a neutrally dynamic stable. But with respect to the time, amplitude is increasing like this, then we can say that it is a unstable, dynamically unstable. Means with respect to the time, it is not at all reaching towards its equilibrium, but it is passing from the equilibrium, but it is exceeding the equilibrium. So this is the two things, and now I am going to discuss about the neutral point, static margin, and also the maneuvering point in the further slides. So I will first talk about the neutral point and the static margin. I can say here that for the neutral static stability, Cm alpha will be equal to 0. Okay, so I have told that Cm alpha means the variation of coefficient of movement with respect to the variation of the angle of attack. If this is 0, dCm by d alpha is equal to 0. This I am writing a small plot here. This you can see here. This is the alpha and this is the Cm. And if dCm by d alpha is 0, it means it is a constant. There is no slope. This is called Cm alpha is equal to 0. No slope. of this curve. If it is like this, we can say that aircraft is neutrally static stable. Okay, so for the neutral static stable, the Cm alpha will be equal to 0. So I have shown here, this is the Cm plus, and it can be here also. It is not only the plus side, it is minus side also. It can be Cm alpha is equal to 0. Okay, so both are the correct thing. So you can see that the Cm alpha will be 0. This equates to a horizontal line on a Cm versus alpha graph as shown in the figure. Next figure I will be showing you. The aircraft will pitch up for any angle of attack condition. This may not seem consistent with the definition of the neutral static stable. Okay, so this aircraft will pitch up. So what happened, I have just told you. So it is hit here and it is making up. It will maintain the same pitch up. That is the meaning of the neutral stable. It will remain in the same condition. Means as angle of attack is changing, aircraft will remain the same pitching state. Okay, so this is called the neutral static stable. So if here Cm naught plus Cm IH were set equal to 0 and we had Cm alpha equal to 0, then the Cm characteristics would remain 0 for any angle of attack. A horizontal line coinciding with the horizontal axis. So this theoretically the airplane could be trimmed at an angle of attack and not return or diverge following a disturbance. So here this you can see here, this is the diagram here I have shown here. This plot here, this is called Cm alpha is equal to 0 and here is the Cm and this is the alpha. So here the slope of this curve is 0. If it is like this, then we can say that it is a statically neutral stable. Theoretically, the airplane could be trimmed at an angle of attack and would not return or diverge following a disturbance. So what is the meaning of this? The meaning of this, just I am drawing here. This is the aircraft and this is flying in this direction. A wind came from this direction, that is I am writing some V additional. It is a gust. This will try to make your nose up. So I am just drawing here one dotted line. This you can see here that this is the dotted line. This is the nose up. It will make the nose up and aircraft will fly in this new condition, pitch up condition. So the condition of neutral static stable is important because it represents the boundary between the static stability and the instability or instability. Okay, so why we have to understand? We know that the aircraft which we fly should be statically stable, then only it can be dynamically stable. But what is the maximum limit? Up to what limit the aircraft can fly? This indication we can get from the neutral point. Neutral point, how much limitations of these limitations of neutral point should be there? So the condition for neutral static stability is important because it represents the boundary between static stability and the statically instability. Okay, so if this is the aircraft, here is the center of gravity and here is the neutral point NP. So this the center of gravity, how much it can travel? Up to here only, up to here. If it is going behind this neutral point, it becomes unstable. So to have the aircraft stable, your center of gravity should not cross neutral point. So that is the criteria for any stability of the aircraft. That is why the neutral point is very important, because CD should not move. The CG will move depend upon the consumption of the fuel, loading of the material, loading of the manpower, and some aerodynamic features. If they are disturbed, the center of gravity may go ahead or may go behind. So if the center of gravity is crossing this limit or crossing, and if the CG and NP, this is the CG and this is the NP, both are in the one point, then that is called the neutral stable. So this is called the neutral stable of the aircraft. So here this we can see that Cm alpha is equal to CL alpha XCG minus XAC. So where this XCG is the distance of center of gravity, distance of CG from leading edge, and XAC is the distance of aerodynamic center from leading edge of the wing. Okay, so like this we have to see that it is okay. So in this way we have to assess now. Okay, so now this location of the center of gravity and the aerodynamic center of the aircraft will results in an aircraft with neutral static stability. As a result, the aircraft aerodynamic center location is also called the stick fixed neutral point, NP. Okay, so location of the center of gravity at the AC. If the CG is at the AC, will result in an aircraft with neutral static stability. If AC and the CG both are in the one point, then it is called the neutral stability. And that point where both are in the one position, then we can say that it is a neutral point. So if XAC is equal to XNP. If the CG is located aft of the neutral point, the aircraft will be statically stable. So just I want to explain you here. This you can see here. If the CG is located aft of the neutral point, so if this is the CG and this is the neutral point, so if in this condition at the neutral point lift will act and this will make nose up and this Cm alpha is positive. So if this Cm alpha is positive and if it is ahead, then it is a unstable, and if neutral point is behind, if this becomes the neutral point and this is the CG, the lift will act here. Okay, so it will be nose down and this will be minus Cm alpha. Okay, so in this way we can find out the location of the. Now we have to see that if the CG is located aft of the neutral point, the aircraft will be statically unstable longitudinally and Cm alpha will be positive. Just now I have shown, and this equation x bar AC is equal to x bar AC wing fuselage plus CL alpha of horizontal tail divided by CL alpha of wing fuselage, neta H, where this is the dynamic efficiency and SH is the area of the horizontal tail, S is the area of the wing, x bar ACH, it is the distance of aerodynamic center of the horizontal tail, 1 minus d epsilon by d alpha, where epsilon is the downwash angle and alpha is a angle of attack, divided by 1 plus CL alpha H by CL alpha W, NH SH by S, 1 minus d epsilon by d alpha. So these equations we have to get it. So this equation, we can find the aerodynamic center and also the neutral point. So this, if we can, this here, it will become the neutral point. If you know these all things, we can get the neutral point. Now, the next point is static margin. So we have discussed till now the this neutral point, and neutral point is depend upon the CG location and the aerodynamic center location, and this gives a margin. As this margin is high, that much we have the static stability. Okay, so here it is very important to understand what is the static margin. So this static margin is another useful concept to longitudinal static stability, is that of static margin of aircraft. We have done this equation previously, and we have find out that mcg, this is the moment with respect to the center of gravity of the aircraft, is equal to L, where L is a lift, and xcg minus xac plus mac. This we have already done in our previous classes. And then cmcg, this is the coefficient of moment with respect to the center of gravity, is equal to coefficient of lift cl, x bar cg minus x bar ac plus cmac. So here, this you can see here in this equation, we have mcg. This mcg we need to convert in non-dimensional form. So how we have to do? So this mcg divided by half rho v square s into c. So here this all will become mcg, will be non-dimensional form. It is called coefficient of moment with respect to the cg. Here is L by half rho v square, it is a cl. So we know that L is equal to half rho v square s cl. So cl is equal to lift divided by half rho v square s. So here lift divided by half rho v square s, this will become cl, and if you divide here half rho v square s, this will become cm, and same way here, if you divide by half rho v square, this will become cmac. So in this way, we need to use the non-dimensional form, because non-dimensional form is easy to understand. It gives a number, and that numbers can be very easily analyzed. We can understand these numbers very well. Okay, so that is the reason we have to use non-dimensionalized number. So here this cmcg, now cm alpha. Cm alpha is what? It is a slope. Cm alpha is, it is a slope of cm with respect to the alpha. So here alpha. So this cm alpha, this will be cl alpha, and this xcg minus xac. And here x bar means, once you write the x bar means it is divided by c. So this x bar is also here, it is a non-dimensional quantity. Okay, so we have to understand that here everything is non-dimensional. We should not use meter, centimeter for this. And also for lift, we have to convert to the lift coefficient. So this xcg minus xac is called the static margin. So here xac minus xcg is called the static margin. So xcg minus xac is equal to, here x, this xac is a neutral point, minus xcg. Okay, so if I draw the aircraft like this this is the CG and this is the AC. So X and P means this, and so distance between, if you take from here, this is the XAC, and from here to here is X and P. Okay, so this XCG. So here X and P minus XCG is equal to static margin. So it is very important parameter, and this gives the aircraft stability. So here SM, static margin, is equal to minus X bar and P minus X bar CG. It means the distance of neutral point minus distance of center of gravity. If it is a minus, then it is a this always will give some minus value, and this minus and this minus, it will become the plus. So static margin is simply the distance that the CG is in front of the aircraft normalized with respect to the mean wing chord. Okay, so how much CG is ahead of the AC. So that is the called the neutral point, this static margin with respect to the mean wing chord. Here CL alpha will be positive for lift coefficient below stall. It can be seen that a positive static margin will result in a negative Cm alpha. So what is the meaning of this? For CL alpha, if it is a positive, Cm alpha will be negative. This is very important conclusion here. So if the aircraft is flying with a less than stall angle of attack, CL will be positive, and this CL, if you see, this is the aircraft. So if this is the CL, and this is from here to here is your static margin. So if this NP or this AC is behind the CG, this will be Cm alpha, and this is nose down, it is called negative. That is why CL will be positive, and if AC is behind the CG, then this will be a statically stable aircraft. That is the meaning of this work. Thus, so these are the conclusion. In this conclusion, we can say that a positive static margin results in a positive longitudinal static stability. So a positive static margin results in a positive longitudinal static stability. So positive means what? This is the CG and this is the AC, and if the CG is ahead of the AC, then SM is positive. So here lift will be like this, lift, and this is called the SM. So this lift into SM, this will give Cm alpha, and this nose down. And this, if this thing is nose down, aircraft will be statically stable. So a positive static margin results in positive longitudinal static stability. So that is the case 1. The negative static stability results in a negative static. So negative static margin. If SM is negative, then what will be the condition? You can see here in this diagram that if your AC is here and CG is here behind, then what will happen? This is negative. This distance is negative. So your moment will be here, Cm alpha, and this Cm alpha will be positive. So positive means nose will go up. In this condition, nose will go up. So aircraft is unstable or negative stable. And the neutral longitudinal stable is associated with when static margin is 0. What is the meaning of static margin is 0? It means this is the aircraft and there is no difference between this is the CG and this is the AC. In the same point, this is the AC. Lift is acting here. So there is no moment. There is no moment. So it will maintain in the same condition as it was given in the disturbed position, and this is called the neutral statically stable. We can see this all things in 3 conditions. If the CG is ahead here and AC is behind, then what will happen? This lift, you have changed like this, and this lift will try to make nose down. So it means the nose down is statically stable. The second case is if CG is ahead, this CG is behind and AC is ahead. So this lift will try to make again, it will go up. The third case is when CG and AC in the same point, lift will be there but there will not be moment. Moment means there should be some distance between XG, the CG and the aerodynamic center. There is no difference. If there is no difference or there is no distance, there will be 0 moment and aircraft will be in the same condition as it was flying. It will not change the angle of attack, or the nose will not go up or nose will not go down. It will remain in the same status as it was flying after disturbance. So next time a plot of Cm versus Cl is drawn here. The derivative Cm/Cl, the slope of a plot of coefficient of movement versus coefficient of lift, which is similar to a Cm alpha plot, is directly proportional to the static margin. The negative of the slope of a Cm versus Cl graph will be the static margin as indicated in the figure. So this you can see here. If we draw the plot of Cm versus Cl here, this is the plot, and if the slope of dCm by dCl is negative Sm, this dCm by dCl is called the static margin, and if it is negative, then it is stable. If dCm by dCl is positive Sm, then it is unstable. If dCm by dCl is equal to 0, no slope, then it is a neutral stable. So in this way also we can find out that aircraft is stable if you know the coefficient of lift and you know the coefficient of moment. If you draw the plot of different ranges and if you see the plot is going from top to bottom, then it is stable. If from bottom to top, it is unstable, and if it is maintaining a horizontal with respect to the CL, then it is a neutral stable. As the CG of the aircraft is moved aft towards the tail, Cm/Cl becomes less negative and eventually equals to 0. When the CG is located at the neutral point, thus the neutral point is achieved when the change of delta E with respect to the CL is equal to 0. Okay, so here I have plotted a diagram of deflection that is called delta E trim with respect to the CL maximum. So here you can see if the plot is horizontal like this, it is a neutral point. If the aft CG between forward CG and the neutral point, the plot will be like this. And if the CG is forward, the slope will be very high. As the CG is going ahead, the slope of delta E trim will be very high. And so you can find out that at this condition, a trim condition is achieved. So in this way, trim versus delta trim versus coefficient of lift plot, and here the CM versus CL characteristics of the aircraft. By this, we can find out how much trim angle of the aircraft is required. Next, we have to see how to find out the neutral point. It is very important for the pilot to understand that where is the neutral point and how much he has to shift the elevator. To determine the neutral point location in flight test, a series of trim points are flown with several different center of gravity location to generate curves similar to those presented in the figure. Of course, the aircraft is not flown with the center of gravity at the neutral point because neutral stability would result. The location of the neutral point is extrapolated by plotting the slope of each delta E versus CL line for each center of gravity location with respect to the center of gravity location as illustrated in the figure. This you can see here that delta E versus delta CL versus the center of gravity location. So here this is the case 1, it is a forward center of gravity, case 2 is a mid, and case 3 is aft. So I am drawing one model, and this you can see that this is the CG, this is the location 1, this is the location 2, and this is the location 3, and here is the CG. Okay, so in this 1, 2, 3, we have to find out delta E by delta CL with respect to the location of the center of gravity. Here, this is the 1, this is the 2, and this is the 3, 1, 2, and 3. In these 3 conditions, you can see that we have got this 1, 2, and 3. If we extend this with a straight line, we will get a point, and this point is called the neutral point. So here, if you extend this, this is here, this is called the neutral point. So in this way, we can find out the location of the neutral point, which is very important to understand the stability of the aircraft. And every pilot, they are instructed in their instruction manual to follow this condition. And as an engineer of aeronautical engineer, we have to get these points for design aspect of the aircraft. Okay. So here longitudinal maneuvering flight includes maneuvers where the load factor is not equal to 1 and the aircraft has a pitch rate. So if the lift is not is equal to weight, so means the N, this is load factor N is equal to lift by weight. So if L by W, L is not equal to W, or it is more than this W, then we can say that it is a pitch rate. Typical maneuvering flight involves load factor about 1 where the aircraft is pulling G. To do the analysis of the maneuvering, one additional term called the pitch damping derivatives to be included in the CM equation. So these CM equations are given here. So this CMQ, if you see here, the term CMQ, these terms provides a damping moment that opposes the pitch rate of the aircraft and acts like shock absorber. It results from the incremental change in horizontal tail angle of the aircraft because of the aircraft has the pitch rate. These things, a diagram is shown here. A positive nose up pitch rate on the aircraft, that is Q1, produces a downward velocity at the horizontal tail, that is Q1XH. This downward velocity produces an increase in the angle of attack at the horizontal tail. So this delta H, which is Q1H divided by U1. So here is the moment Q1. This is the delta H which is produced, and here is XH. So this vertical velocity is Q1 XH and divided by U1. This is the horizontal free stream velocity. So this much angle we will get additional in the tail side of the aircraft. The increased angle of attack in turn produces an increase in lift, which results in a nose down movement opposing the direction of the pitch rate Q1. This is where the pitch damping effect comes on. So here we have defined this angle of attack alpha h, which is alpha plus IH plus tau E delta E minus epsilon, and this tau E is equal to dou alpha h by dou delta E, and in this way we can find out the maneuvering. This thing must be added to expression on this. So in this way we can get this equations. We will have a negative sign which indicates the increase trailing edge up elevator. So these are the references which I have referred in this H out. We can see here that maneuvering point. This maneuvering point is located aft of the neutral point because the aided damping provided by the CMQ provides more stability for the maneuvering flight case. CMQ essentially makes the aircraft appear to have a more negative CM alpha. I am referring these books, Introduction to Aircraft Flight Mechanics by H. Out, and this Nelson RC, Flight Stability and Automatic Control, and NPTEL lecture by the Professor Ghosh from IIT Kanpur. Thank you very much for joining this class.
Like, share and subscribe. Hit the bell icon for more updates.